Hello, so continuing on this weekly contest 326, this week's contest, the third problem, which is partition string into substrings with values at most k. So what this problem says is we get a string s that has digits from 1 to 9, and we get an integer k, and we have this definition of s being good as in where each digit of s is part of exactly one substring. So we'll partition the string, and we call this partition good if each digit of s is in exactly one substring, so in one partition, and the value of each substring or each partition is less than or equal to k, and we get k as input. And the goal is to return the minimum number of substrings or partitions in a good partition according to this definition. And if we can't do that, if we can't divide the string in a way that we get a good partition, then we're going to return -1. Okay, and then a couple of things here so the value of a string is its result when interpreted as an integer, right? So the value of the string 16 is 16, right? Or the value of the string 123 is 123, right? Yeah, and here they are just defining a substring as a contiguous sequence of characters, right? So that's pretty normal. So let's take a look at the example here. So for this example, k is equal to 16, right? So we can't do 165 because that's bigger than 16, but we can do just 16, that's bigger than 60, that's smaller than 60, so it's valid. Because the problem says it has to be smaller or equal, I think. Yeah, it has to be less than or equal. Okay, so that means that 16 here is valid, so we can make that the first partition, but we can't do 165. Is 54 valid? Yes. Is 5 valid? Yes. Is 54 valid? Yes. Is 546 valid? No. So we stop here. 54. And then we go 6 valid? Yes. Is 622 valid? No. So we stop there and then we take 2. So overall it's 4. Right? Here it's not possible because just there is one digit 8 here that is bigger than 5. So even if you take it alone, it won't be valid. And if you even try to take it with another number, it would be even bigger, so it won't be valid. 18 is not valid, right? So there is no way to do a good partition because of the number itself is bigger than k, so return -1. And yeah, so that's pretty much the idea here. You can see the string length is 10 to the power of 5, so that really rolls out any oven squared algorithm. Or and k is 10 to the power of 9, so that also rolls out like any oven k solution, right? So how can we solve this? Okay, so how do we solve this? So the easiest way to think about it is like this. So let's take the first example, and k is equal to 16, right? Since 1 is valid and 16 is valid, both are smaller than k, would it make sense to ever take 1, right? Instead of 16? And the answer is no, because what we want is we want to minimize the number of partitions or the number of substrings. And if we take 1, we will only increase the number of partition because maybe the next number it won't work because you can take 65, right? You have to take 6 alone. So instead of taking 2 in one partition, now we are taking 2 separately, and we have to adding 2 instead of one partition, right? And you can play with different numbers. Like even if you do 1, 2, it's still good to take 11 than to take 1 and 12 here, right? So even if you take just 1 here and take 12, you could still take 11 and take 2, and you will end up with the same number of partition. Let's say we had 112 and k is equal maybe 13, right? You can't take 112, but you can either do this or do this, right? So even in this case, it's still optimal to take as much as you can first because it will be equal to just taking 1. But you definitely don't want to take each one separately, right? So that's sort of where the greedy idea comes from, is that let's try to take the partition, to keep extending the partition as long as we can. And then only when we can't start a new partition. And you can come up with a couple of examples to prove it to yourself. So for this example, if we try it here, 5, 4, 6, 2. So what we'll do, k is equal to 16. Okay, so 1 is still smaller, so we try to extend. If we extend to 16, it's still valid, so let's try to extend again. So if we try to extend to 5 though, it's no longer smaller, so it's no longer valid. So let's just pick this as our partition then. So this would be partition 1. So we start a new partition now at 5. 5 smaller, good. Let's try to extend it. 54, we can extend it, it's smaller. So let's try to extend it more, 6. Now 546 is not smaller, so we can't extend it, so let's end our partition here. So now we have a second partition. 6 is smaller. Can we extend to 62? No, we can't, right? And so we stop here. This would be the third partition. And then we try this second one, 2, smaller, 4. So we have 4 partitions. Now, another variant you might try is to say, okay, since I want to avoid this 62 here, let me maybe do this partition and do this one alone, and then that way I can't do 65, I have to do this and then do this. So it would be partition 1, 2, 3, 4. So still 4, right? Because you can't take more than 2 digits here, right? So you can play with it different, just to prove to yourself that the greedy will always works. So may as well just go with this deterministic approach. We will keep trying to expand the partition until we can't anymore. And to do that, we can just do it with 2 pointers, right? I and j. And as long as the string from I to j integer is smaller or equal to k, smaller than k, right? We can keep going. But if it's bigger than k, we have to count this partition that just ends at j. So we have to count the partition that ends at j and then start a new partition from j. Or maybe, yeah, from j. You can also say, from j, because it's up to j that is bigger than k. So that means from I to j minus 1 is a valid partition, right? Because we kept extending, right? Otherwise, if it's still smaller, we'll just keep extending our partition by using j plus 1, right? So that's roughly the idea. We can use 2 pointers, and we keep extending our partition as long as we can. And every time we can't anymore, we start a new partition. There is only one thing that we saw in the second example that we need to take care of, which is 3, 8, 1, 8, 2, and k was equal to 5. So because this 8 is bigger in this one as well, there is no use in trying to make a partition, because we can never make a valid one, because we have to include this 8 in some substring. It can't alone, it's not valid. With another digit, it's not valid either. And so if we have to check if any digit is bigger than k, then there is no valid partition, so we can just return -1. Okay? So that's just one thing. Other thing we need to take care of first before starting the calculation of the partitions here. So let's implement this and make sure it passes test cases. Okay, so let's implement this. So the first thing we want to do is, if there is any digit, right, that we saw in the overview. So if there is any digit that is bigger than k, okay, for d in s, then we're going to return -1. Otherwise, we start our 2-pointer solution here. So 0, 0 for both I and j, and we'll keep going as long as j, we haven't explored the entire string. And so we will check the substring. So this would be our current partition is from I to j. So in Python, that would be +1 here. So this would be the substring that we'll check. So if this substring is bigger than k, that means we can't extend up to this j value, right? So let's count this partition ending. So this would be basically counting partition ending at j -1, right? Because if we include j, it's not valid. And so we will start a partition from j, right? But otherwise, which means it's smaller or equal, that means it's still valid partition. So let's just keep extending. Okay, and we need to just define our count here to be equal to 0 initially. And this we'll need to convert it to an int because s is a string initially, so that we can do this comparison here. Now in the last one here, we shouldn't return just count, we should return count plus 1. Why is that? Because remember, we increment only if we find a number that we can't extend to. So at the end, when we are at the final number, we won't reach this, right? Okay, and so we will need to account for that last number, and so that's why we are doing this plus 1 here. Yeah, so that's pretty much it. So let's just run this, make sure it passes. And let's submit. And looks good, accepted, right? Now in terms of time complexity, you can see here each time we either increment to j or we move I to j, right? So roughly at most this is going to be O of n. Now if you want to just prove to yourself that this is O of n, you could also just do this in the else, because we already know that our partition is starting at j, so we can just increment to j immediately to go to the next one and check, right? Because we know each single digit would be valid, because if it was invalid we will catch it here. So this should work as well, and it will make it easier to assess the time complexity. So that's accepted. Now in terms of time complexity, we can see on every iteration we do j plus 1. So every iteration we move j and we stop when j reaches the end. So we know this is O of n because of that, n being the length of s. This is also O of n, it goes through every digit in the string. So O of n time overall. Now in terms of space, we are only using this extra variable but nothing else, so this would be O of 1 space. Yeah, so that's pretty much it, I think, for this problem. Main idea here is 2 pointers and greedy, but where we keep increasing our partition as long as we can. Yeah, so please like and subscribe, and see you on the next one. Bye.